So in quantum mechanics, elementary particles have no definite position or velocity. Instead, the state of the particle is governed by its wave function. And so the wave function is actually something whose square is a probability distribution. So if the wave function, we call it psi of xt, then the idea is that if we look at the square of its magnitude, then this gives us the probability density. The probability density function for the distribution of where we might find this guy. So in other words, the probability that the location of this guy turns out to be between A and B, so that is, so it occurs somewhere in some interval from A to B, then this would be the integral of phi xt quantity squared dx. Okay, and so because this is a probability density, we know that the magnitude squared needs to be between 0 and 1, and also that the integral of the magnitude squared needs to be equal to 1. So that's just a fact that it's a probability density. And so this, with no other bounds, we can assume that this is an integral over R. Okay. And then just as a side note, the idea here is that psi can take complex values. So in general, since it can take complex values, then you actually have to talk about that the magnitude bars there. So you might have been looking at this and saying, hey, we're talking about the integral of that thing squared. If we're squaring it, why does there need to be an absolute values? Because the square of anything is going to be a non-negative number. Well, not the square of an imaginary number, right? So in fact, here this magnitude squared of psi, this is actually psi times psi conjugate. So if you're not too familiar with complex numbers, don't worry a whole lot about it. We're not going to use them a whole lot in this course. But the basic idea is that the set of complex numbers C, this is basically just R2, the plane, where we've also defined a way to multiply two vectors. So in general, you can multiply a vector by a scalar. That's fine in any vector space. But you're not really allowed to multiply two vectors against each other in a nice way. There's the cross product, but that's specific to R3 and has a couple of strange algebraic properties when you look at it. So the way it works is as follows. Okay, so let's see. So what does a complex number look like? So like I said, it just looks like a point in the plane. And so if we have some point here, say this is our complex number z, then it has a real part, a, so a is the real part, and over here it has an imaginary part, and so we've got a real axis, and we've got an imaginary axis, and z looks like a plus bi. So you can think of this as being the point with coordinates a comma b. That's totally fine. And then the idea is that we've just used a different basis to denote this. So you can think of the standard basis decomposition of this vector as being a times 1, 0 plus b times 0, 1. And so what we've done in the present situation is we're just calling this first basis vector by 1 and this second basis vector by I. And so then it ends up being a times 1 plus b times I. And of course, we don't actually write the 1 part, so it just looks like a plus bi, right? So that's your complex number. And then the notion for multiplication that we have is, so if you've got AB multiplied by CD, then the definition for this is that it should be AC minus BD, and then in the second coordinate, AD, D plus BC. And that looks just completely crazy until you realize that it corresponds exactly to foiling. So if you have A plus BI times C plus DI, then multiplying this out, we have AC plus ADI plus BCI plus BDI squared. And then you realize, oh, I squared is minus 1 by definition. And so if I collect up the real and imaginary parts, the real part will be AC minus BD, and the imaginary part will be AD plus BC. And so that's where the multiplication formula comes from. So the only other thing we need to know is what the conjugate is. So the conjugate or complex conjugate of some number z with real parts a and b is, so it's denoted by a bar, z bar, and it's defined to be a minus ib. So in other words, you just negate the imaginary component. And so let's look at that geometrically. So we'll come back to this picture here that I drew, and let me move this real and imaginary part here out of the way a little bit. So the idea is that if we come down here to minus b on the imaginary axis, then this is where we would find z conjugate. So in other words, conjugation, taking the conjugate of a number, it just reflects it vertically across the axis. So for instance, if I had some point, say over here, if this is w, then this is going to be, actually here, let's make this w, and then this would be w conjugate. So it would just be flipped over the bar, that kind of thing. And the conjugate of a is a. And that's, by the way, that's the definition of a real number. It's a complex number whose conjugate is itself. Anyway, so let's see. So with that, then if I look at z times z conjugate, I've got a plus bi times a minus bi. And multiplying this out, I'm going to get a squared plus b squared. And so going back to my diagram here, if I look at this triangle right here, then the magnitude of it right here, so that's the magnitude of z, that's going to exactly be a squared plus b squared square rooted. And so in general, the formula is that the magnitude squared of a number is the number times its conjugate.